welcome back to the course Cobotics Theory and Practice, Module 2, that is Actuators, Sensors and Safe Workspaces. In this lecture, we'll discuss about BLDC motors and permanent magnet synchronous motors. Those are commonly known as AC servo motors. Okay, so overview of this lecture goes as this. We'll start with introduction, that is construction of a BLDC motor, the working of a BLDC motor or actuator, BLDC motor driver, schematic of that, how it works, we'll discuss. We'll have a brief introduction on AC motors, that is through its advantages and disadvantages. We'll see the working principle of a synchronous AC servo motor, synchronous motor drive systems, that is variable frequency drive, we'll discuss on. We'll discuss position speed control scheme for PMSM or BLDC motors, torque control scheme for PMSM and BLDC motors. So, let us continue with BLDC motors and actuators. We will discuss construction, working and drives. So, as such BLDC motors, there is a significant difference between the way it is constructed as compared to the DC motor that we have discussed in the last lecture. So, conductors and the armature is fixed. Here you see these are the conductors, these are the copper coils which you can see here, that is fixed and that is stationary and it is mounted permanently to the station. Okay, and you have a rotor, this is the rotor, that is the armature, that contains the magnets. So, these are the magnets, magnets are glued all around. Okay, so armature is fixed and magnetic field on the rotor moves. Okay, the center spindle that you see, that actually goes inside here, so it is fitted on top of that. Okay, it may include Hall effect sensors to give position feedback and synchronous motion. So, in these motors, as because the stator contains all the copper windings, all the heat is generated at the stator is dissipated out easily. So, there is better heat dissipation from the stator and you do not need to do make and break kind of commutator arrangement which is there in the armature of a DC motor that you saw. Over here no make and break circuit, no commutator is there, current is directly put to the windings which are creating the magnetic field. Okay. The rotor has now reduced moment of inertia. Now the rotor does not carry the coils, that is very light. So, that is the reason it has very good torque to weight ratio. The torque which it can generate for a comparable size of DC motor, as because it does not have any commutator. So, they are very light for the same torque. Okay. So, the rotor is light as well, because you see the rotor has only the magnets, not the commutator. So, that is very light, so it picks up the speed very fast. Okay. It is more durable and have longer life because there is no make and break circuit. So, there is no arcing and there is no carbon brushes which gets wear out. So, low maintenance is required. So, it has lower mechanical loading because of low mass of the rotor. It has improved safety as because there is no make and break circuit which is there. So, there are no electrical sparks. So, they are very safe for the environment, inflammable environment like a robot doing some painting operation and those kind of environment. There are no brushes, so it is very quiet also, there is no noise. A smaller dimension as compared to comparable power, they are inexpensive and have low maintenance cost because you do not have carbon brushes which is required to be replaced after every few running hours. Center hollow design is possible. This is very much required for cobot. Cobot needs all the wires to be passed from within the robot, that needs a center hollow shape, and that is very easily possible with these kinds of motors. So, applications are many: robots in inflammable atmosphere, aerial robots which needs a very high speed to be generated quite quickly, electric vehicles, cobots. So these are some of the applications. Disadvantage is only one, they are expensive because of its control system, the kind of winding which is there and the kind of sensing which it has Hall effect sensors at 3 places also, and switching circuitry is little bit complex because of 3-phase winding which is there. We will discuss in detail. So these arrangement would cause little higher cost for these motors. Okay. So let us see how this motor works based on the rotor position in the sector, how the Hall effect sensor can give me the position. So where are the Hall effect sensors located? Whole of the motor, let us say it is divided into 6 sectors. So every alternate sector has a Hall effect sensor. So if it is sector 1 here, sector 2, sector 3, sector 4, sector 5 and sector 6. So there is a Hall effect sensor here which is called as A, Hall effect sensor which is here, Hall effect sensor B and Hall effect sensor C that lies here. Okay. So let us see how it can communicate the position of the rotor. Let us say if at all there is this is your rotor which has a magnet. So this magnet will energize Hall effect sensor. How? So if at all it is located here 100%, okay, let us say your armature is here, this will cause Hall effect sensor A to be completely energized. These 3 bits will actually show the state of Hall effect sensor A, B and C, 1 for active, 0 for inactive. So when the rotor is at this location, what happens? Sector A Hall effect sensor is fully energized, whereas B and C is taken as 0. Okay. Hall effect is a gradual sensor, it gives you an analog signal that needs a thresholding device to actually convert it to digital signal. Okay. So based on the signals, this will now give a high signal of 1. So effectively this gives you 1 0 0. If I convert it to binary to decimal, it is equivalent to 4. So whenever it is at this location in the sector 1, it will give me 4 if 3 bit converted to decimal. So what happens when it is here? This energizes Hall effect sensor A and B both, and C which is quite opposite to it, this remains at 0. So this will give me 1 1 0. When this is converted to decimal, it is equivalent to 6. Now when it is at this location, so sector A, this is 0, Hall effect sensor B will give you 1, Hall effect sensor C again that gives 0. So it is 0 1 0. So this when converted to binary to decimal, it is 2. So likewise, so for each and every position in any of these sectors will give a unique value of Hall effect sensor. Okay. So like for example, if it is here, you see, because it is 100% opposite to Hall effect sensor A goes to 0, B and C gets energized and this gives you 0 1 1. Likewise, so wherever is your armature is lying, this rotor which has a magnet lies, accordingly it can tell you the approximate pose of your rotor. If it is in any of these sector, you can get to know. Okay. So depending on that, you energize the coil which is next. This is a closed loop kind of operation. Okay. So what happens when it is at minus 30 to plus 30 degree, that is in sector 1. Okay, sector 1, what you do? You switch off the coil phase A and A bar is made to go 0. Okay, what about B and B bar? You switch on B and you also switch on C bar. You also switch on C bar. So when it is at this location, you switched on this and this so that you get a effective pull along this direction. Got it? So now when, let's say if it is at sector 5 210 to 270 degree over here. Okay, so you should energize B bar and A, B bar and A. That means A is energized, A bar is 0, okay, and B bar 0 1, that means B is 0, B bar is 1. So it effectively gives me A and B bar as high, and as because it is in this sector already, so that is made to 0. So what you do actually, wherever is your rotor is located, okay, in any of the sector, you energize the next two sector coils so that it gets a pull and finally it moves in that particular direction. Okay, so in this case it will move like this. Okay, so in order to rotate it in opposite direction, the reverse thing has to be done. If it is here, you switch on 6 and 5. If it is at 6, switch on 5 and 4, likewise. So the coil can be energized based on you want to take it in clockwise or counterclockwise direction. Accordingly it is done. So now how that effectively is implemented here. So making A or A bar high means, if at all there are three phase coil which are connected like star which is shown here. So when A is on, A bar is off, so this becomes a positive wire. Okay. Similarly, when B is on, B bar is off, so what will happen? This will become positive. Okay. If B bar is on, what will happen? If B bar is on, if this is on, this will become negative. So any single wire can be made positive or negative depending on A bar, B or B bar, C or C bar, whichever is connected. Okay. So these 6 switches can control the polarity of the 3 wires which are here. So effective state, if you can see, this is 3 phase trapezoidal sequence. So all these 3 phases of the BLDC motor will have a voltage which very much looks like a sinusoidal signal. So this can be equivalent to a sinusoidal signal. It is near to sinusoidal. It is actually trapezoidal signal with phase difference of 120 degrees. So if this has a phase of 5, this has a phase of 5 plus 120, this has a phase of 5 minus 120 or plus 240. Got it? So this is how these 3 phases will create a rotating magnetic field in the coil. Okay, and that ultimately leads to the rotor that follows the rotating magnetic field and ultimately it rotates. Got it? And this switching of the coil is done based on the Hall effect feedback, because if your rotor is stuck somewhere due to the load, you should not rotate the pole or else it will miss the cycle. Okay, and slipping will happen. So if it is stuck, the coil is no more rotating the magnetic field. If rotor is stuck, your rotating magnetic field is stopped as long as it does not cross through that. It comes to the next sector, next two are energized. If it is come to the next sector, another two will be energized likewise. Okay, so that is the closed loop kind of operation based on the Hall effect sensor. So depending on the Hall states, you switch on the sectors. Okay, so this gives rise to a rotating magnetic field. So this is how your rotor actually rotates. Okay, and the coil is actually stationary. Coil remains stationary. This is not rotating. This is fixed to the body of the motor. Okay. Now, how that is implemented on a circuit, you see. Here I have shown HIP 4086 chip, which is a 3-phase MOSFET driver. Okay. So this is nothing but a MOSFET driver. These are the MOSFETs which are placed outside to the chip. This creates actually the switches 1, 2, 3, 1 bar, 2 bar and 3 bar, or A, B, C and A bar, B bar and C bar. So these are the 3 wires and this is your motor which contains the coil. Okay, these are the coil which is star connected, which is shown here, and finally it is controlled by a controller which is here, that actually takes in the signals from all the Hall effects. Okay, Hall effect signals are sent to this, and controller converts which one is to be energized, A, B or C, or A bar, B bar or C bar. Accordingly, it sends the signal. Okay, this is the external battery which is used to supply the controller as well as to this chip. Okay, so this is how it is completely made. Okay, whole of this scheme goes like this. So you can control the speed depending on the Hall effect feedback, or whatever is the speed that you desire, you can precisely control. Okay, so using that you can control the speed, and if at all you have a joint angle sensor also, apart from the encoders, Hall effect sensors which are there, apart from the Hall effect sensors which are there, which can give you a rough estimate of your state, where you are 1, 2, 3, 4, 5, 6. So whatever state it is, that is a gross position of your router. You can also have a precise angular feedback using some kind of sensor, and you can make the control very precise. Okay, so this is how a typical BLDC motor driver works, and this is implemented over here in this circuit. This is Intercell. This is a company which makes such. There are many such similar company which implements HIP 4086 driver, 3-phase MOSFET driver. So you see, this is the programming port which is actually to program the microcontroller which is here. So this is the microcontroller and peripherals which is here. There is also a current sense circuit which is here, which can control the current. These are the power MOSFETs, 3-phase, 1, 2, 3, 4, 5, 6. So 6 MOSFETs are here, that is actually creating the 3-phase bridge. Okay, this is the HIP 4086 MOSFET driver that is there. This is a buck regulator that is actually communicating all the required voltages to the driver chips and the microcontroller. This is for Hall effect supply, that is 5-volt supply that goes to the Hall effect sensor. Okay, then you have phase A, this is for phase B, and this is for phase C. 3 different phases are connected here. This is for the external power source, that is actually the real power source, not for the control, that is to drive the coils. So whole of that implementation that I showed here is made here, and ultimately you get your BLDC motor driver. This is a closed loop operation because it also uses the Hall effect sensor as a position feedback. It can just run the way it is used in quad rotors, and there is no feedback kind of BLDC motors drive. So those are known as ESCs, electronic servo controllers. They have just 3 wires to trigger the 3 phases, that's all. Okay, it doesn't have feedback from the Hall effect sensor. So those actuators, they don't have feedback, they run on an open loop because the load is not variable. In case of quad rotors, the load is not variable. You precisely know how much load which is going to come. Accordingly, you select the motor of precise torque, little higher torque actually, okay, so that it never fails, it never slips. Okay, and whatever the angular velocity you command, it actually goes there. You don't need a feedback because your rotor doesn't stuck anywhere, it is not overloaded anytime. But in case of cobots, you also need a Hall effect sensor. Where is your rotor? You need precise feedback before you switch on the next 2 coils. Okay, accordingly it is made to run. It also has a precise angular feedback sensor which will give you precise angular control also. Okay, now let us come to PMSM, that is permanent magnet synchronous motor. Okay, that is a 3-phase AC motor. Let us see the working principle and the drives that goes to these kind of motors. Whatever motor which is there in a standard industrial motor, they are normally PMSM kind of. Okay, now the operation goes as AC supply is directly connected to the electromagnets that creates an alternating poles. Okay, the magnetic field generated due to the set of stator coils. Again, over here the stator coils are outside, okay, and your rotor, which has permanent magnets, they lie inside. Okay, so this is not like your BLDC motor. BLDC motor has a stator which has coils which is stationary. Over here you have coils which is again stationary, but it is coils are outside, and you have permanent magnet rotor which is inside. Okay, so the main design, it is inexpensive due to less number of parts, just like BLDC motor. It has convenient power supply because AC supply is readily available anywhere. You just need a transformer, step it down, at least 50 Hz is easily available. No commutator and brushes like DC motors, and associated problems of arcing and wear, which requires quite frequent maintenance. Take up less power because power is not dissipated at the commutator. Okay, rotor inertia, low rotor inertia, that makes it responsive. This time rotor doesn't have the coil, just like DC motor, this doesn't have a coil on the rotor. So what happens, rotor has the magnet. Only difference that I see is the rotor has a magnet that was outside in case of BLDC motor. Over here the rotor is inside, and that also has a magnet. Okay, in both the cases you have equivalent three-phase supply which is creating a rotating magnetic field. So PMSM is very much similar to a BLDC motor. Only thing is you have rotor which is placed inside here. In case of BLDC it was outside. So the rotor has low inertia, and that makes it responsive, just like BLDC motor. They are very reliable, robust and easy maintenance, and they have long life. Availability of wide range of variable frequency drives are there. What you need here is a variable frequency drive. That is what we will discuss now. Due to its simplicity and ease of use and low cost, it is widely used in all modern industrial robots. Okay. So now how it works, let us see. So three phase is directly supplied to the coils which are stator coils. Okay, if three phase is supplied to this, if this has a phase of psi, this has phase psi plus 120, and this has phase psi plus 240. Okay, so what happens, it creates a three phase supply like this, and this will gradually rotate the magnetic field like this. So if this coil is energized, this coil is fully energized after 120 degree. Okay, that means this magnetic field rotates at a frequency of the electricity, three phase electricity which is supplied. So the supply voltages may be written as V is equal to V0 sin omega t plus phi. Phi is the phase. Phase angle is 0 degree, 120 degree and 240 degree for each one of them. Those are fixed, and omega is the frequency of rotation of the magnetic field. V is the peak voltage which each of the coil would see. So this three phase stator winding carry three phase currents that produces three phase rotating magnetic flux, and therefore the rotating magnetic field. The rotor is provided with a DC supply, or it has a permanent magnet which locks in with the rotating magnetic field, and they rotate with the synchronous speed of the rotating magnetic field. Got it? So whatever is the speed of rotating magnetic field, that becomes the speed of the locked in armature which is having the permanent magnet. So permanent magnets get locked to the rotating magnetic field, and it rotates at the same speed. Once the rotor is in operation, the speed of the motor is dependent only on the supply frequency. So whatever is the frequency which is there for the rotating magnetic field, that becomes the speed of the rotor. Okay. So yes, there are many disadvantages also. It can overheat on long operation. If you rotate it little slower, it may not pull up that much of air inside, or there may be little bit of overheating which can accumulate and make the motor little hot. In case of industrial robots, you have very good heat dissipation, but in case of cobots, the whole of the rotor is caged inside, so heat may not dissipate so well. So normally BLDC motors are preferred in those cases. It can overheat in long operations, so they are normally used in industrial robots, which you see there is a sign that it may get overheated. So heat symbol is there. So now let us look at the whole driving system, how to change the frequency, because you see whatever is the 3-phase AC frequency, that becomes the speed of the synchronous machine, that is the PMSM motor which is here. So you have to input the 3-phase AC supply, that is 50 hertz in India. Okay, 3-phase AC is inputted. You have a 3-phase rectifier which is nothing but a bridge rectifier, and finally you get a positive over here, negative over here. So you have from 3-phase AC signal, you have converted it to a DC signal with a ripple. These are the ripples. Okay, that is bound to happen because you see you have just mirrored the low side to the higher side. Okay, so you see only the higher side of it. So all those are here. So you see continuous positive here, negative here, then it is filtered and a pure DC kind of power is generated here. So till here it is nothing but an rectifier. Now what is done, you have a 3-phase PWM inverter. So this is nothing but an inverter. What is its role? Basically it has again 3-phase bridges, the way you saw it in case of 3-phase switches. Okay, so you have A bar, B bar, C and C bar switches. Okay, so if you switch on A, this wire will go positive. If you switch on A bar, the same wire will become negative. So accordingly each one of these wire can be made positive or negative, A, B or C phases of the PMSM machine. Now instead of making it continuous high or continuous low, you create a equivalent voltage signal. That means what is done here is, in order to regulate the level of voltage in the positive side of A, what you do, you create a PWM with 0 to 100% duty cycle from here to here, so that you see a equivalent voltage rise that is there in the A wire. Let us say if it is A only. So each of them will carry a PWM that creates a equivalent voltage ranging from 0 to 100% duty cycle, 100% to 0 again duty cycle, and again A bar is switched on and you do the same thing, 0 to 100% duty cycle and 100% to 0%. That means in both the positive half and the negative half, you make 0 to 100% sinusoidal wave. So effectively this creates a feel of an complete sinusoidal wave. So this is how equivalent voltage is generated in the phase A, which is equivalent to the signal that you want. Okay, so each signal should be at a phase of A. If it is 0 degree phase, this one should be at phase of 120 degree, the C should be at 240 degree. So 3 different sinusoidal waves are created using 3-phase PWM inverter, which effectively goes to the PMSM motor. So what happens? This is a 3-phase signal for which the frequency you can control based on the inverter frequency. So now a constant frequency is converted to a variable frequency. That is the reason it is known as variable frequency drive. So you saw how a rotor gets locked to the rotating magnetic field and how a variable frequency can be used to create magnetic field with different rotation frequency. Okay. So, this is how this motor speed can be controlled. Okay. Now, if you can control the current that effectively goes here, okay, current that goes here, let me use a different color. So, this is it. So, if you can control the current which is actually flowing through this wire, then you can control the torque as well. So, there is a DC chopper drive, again a chopper drive which is here, that can control the torque of this PMSM machine. So, you can have a similar type of chopper drive which can control the torque. Speed can be controlled by controlling the frequency of the variable frequency drive, and direction you can just reverse the direction of omega, that is the cyclic frequency of the 3-phase, that motor direction can be reversed. Okay. So, this is the way you can control the speed as well as torque and direction. If you have a position feedback, then you can have an external controller which can create a closed loop and can control the precise position of these kind of motors. Okay. So, this is how position, velocity and the torque of such motors can be controlled. So, now synchronous AC machine, there are some special features, various types and applications, especially useful in applications that requires precise speed or position control, especially robot. So, speed is independent of load, you see, whatever is the load, your rotor will rotate at the locked in frequency along with the frequency of the rotating magnetic field over the entire operating range of the motor. Okay. So, speed is independent of the load. Speed and position may be accurately controlled using open loop control. So, you see, whatever is the frequency of rotating magnetic field, that becomes the speed of the rotor also. Okay. So, speed can be precisely controlled even in open loop. You do not need to have a closed loop. There is no slip, you see. Why? Because the load is predetermined and it is well calculated before selecting this motor. It can hold its position with static magnetic field. Let us say each of the pole has got fixed magnets, electromagnets, with the current that is coming to it. So, it will create a resultant magnetic field which is at a particular direction, rotor will align itself to that particular direction. Okay. So, it can hold its position also. So, omega can also become equal to 0, frequency of rotation of the magnetic field. If that is static, that goes to 0, rotor gets locked. Okay. Increased efficiency in low speed application also, like in case of ball mills, but yes, in low frequency the motor has tendency to get heated up. Okay. So, applications are many. It is mostly low power precise robot actuators, turntables, linear rails, CNC machines, they require such kind of precise speed and position control. Types of variable frequency drive, it can be voltage controlled or it can be current source inverter. These are very common in robotics. That depends on if you want to control just the speed or you want to control the current also, that is to control the torque of the motor. So, controller types are PWM scalar control, field oriented control, that is the vector control, this is most common one in robotics, and direct torque control also. Okay. So, yes, the whole of the control loop looks like this. When you have to control torque, speed as well as position, so the control loop looks like this. This is your robot system which has nothing but motors within, okay, that actually runs the links and finally gives you the joint rates and the position. So, both of them can be obtained from the same kind of sensor. A position can be differentiated to get the velocity, angular velocity. So, it gives you the velocity feedback and the position feedback. Okay. That is compared against the desired position, desired and position actual is compared, error is calculated. So, you have a position controller which goes in here, normally PID controller, that generates the reference speed, that is theta desired dot, that is the theta desired dot, that is rate of change of joint angle that is required is here, and this is the actual rate of the motors which you are controlling. So, desired velocity, actual velocity, take the difference, will create a reference error here. This error is put to the speed controller here. This again is a kind of PID controller. This generates the commanded torque, that is the desired torque that has to come here. Now again you may have a current sensor that gives you the calculated torque over here, that is the actual torque based on the current sense can be compared with the desired torque. So, actual torque here and the desired torque here can be compared, and that goes to the torque controller here, and finally the current goes to the actuator controls the robot. So, this is a closed loop scheme which can control the position of the robot joints. So, actually at each stage there is a additional input, you see this is a desired trajectory input. From here you can directly feed in, even if it has achieved the desired position, you want to go at a certain velocity. So, direct velocity input can be fed here at this location. Okay. Direct torque commands can be given here. So, even with the balanced torque of the desired and the actual, you want to run the motor directly with the torques. So, you can directly feed in the torque here, and torque is inputted directly to the torque controller and it goes to the actuator. So, you can make the motor run in position mode or in the torque mode depending on where you are feeding in the inputs. Okay. So, the synchronous speed is actually 120 F by P. You see these motors, they do not just have 3 poles, they have multiple poles. So, if F is the frequency of the AC supply, that is the inverter supply, P is the number of poles, so synchronous speed in that case would become 120 F by P revolutions per minute. Okay. P is the number of poles. Okay. So, slip rate, if at all slip is occurring, so in that case slip rate is there, that is synchronous speed minus rotary speed by synchronous speed. Okay. So, this is the slip rate which normally should be equal to 0 in case of completely synchronous machines like robots. So, you do not expect slip to happen. Okay. Okay. If at all you have to run in control scheme which can control torque, in that case you can simply trim off everything which is here, and this is a equivalent circuit for that. In this case you can directly feed in torque here. Okay. Torque should be clamped based on the maximum torque that is achievable by the motor. Use the torque constant to convert it to equivalent current signal, that is Km. If you remember, Km into Ia is equal to torque. So, you do the other side of it. If you want the torque, you divide by torque constant Km, what you get is I. So, this is the desired current to achieve this torque. This current again is clamped based on the maximum current that this controller can take, that goes here. Okay. So, again you have feedback for the position, encoder used over here to take in the position feedback as well as the current feedback so as to control the current. So, this is a combined controller for the internal current loop that can control the current precisely, and finally this voltage goes to the PWM inverter, that is a 3-phase inverter which can control the rotating magnetic field speed that generates the 3-phase currents to the motor, and motor runs. It creates the torque that goes to the joint. Okay. So, this is the control scheme for torque control of permanent magnet synchronous motor or a BLDC motor. Both uses a kind of inverter based circuits to run. Okay. So overall, let us just recap for the cobot joint, the actuator encoder ring which is here, these two will be discussing next in the next lecture, that is the sensors, okay, frameless, that is the BLDC motor or permanent magnet synchronous motor with the kind of electronics which goes in, okay. So few things are covered, few are remaining, that we will be doing next. Accordingly, we'll at the end we'll fulfill everything, that is harmonic drive, sensors and the actuators, and some mechanical design also we'll discuss and we'll complete this. Okay, so this is what we'll be discussing next: torque sensor with digital interface and link position sensor. Okay, we have just covered the drives that is there to run two different kinds of motor. Okay, so in the next lecture we'll be covering sensors, position sensor, velocity sensor, acceleration sensor, and different kinds of sensors that are used for force measurements. That's all. Thanks a lot.